Hi everyone, welcome back to another physics webinar. Today's session is going to be carrying on our nuclear physics topic. So today we're going to be looking at how we can use nuclear radiation in medicine. This session will be an hour long as always, and it will be uploaded onto YouTube later on, so you can have a look, refresh, revise, and take down any notes that you didn't get. So if you don't know me already, my name is Preshayla. I study physics at Loughborough University and it's my 4th year as a tutor. So what we're going to cover today then is what can we use radiation in medicine for, understand 4 different applications of radiation in medicine, so the 4 that you need to know, understand how we can reduce our risk of radiation, and understand what nuclear fission is and the features of a nuclear reactor. So we're going to be looking at 2 main concepts today, radiation in medicine and then fission. Okay, so let's summarise what we did last week and that first half of nuclear, really understanding what alpha, beta and gamma are. So this was Tuesday's webinar, so 1 week ago. So we looked at what stops alpha and beta radiation, we looked at paper stopping alpha, foil stopping beta, and then lead or concrete stopping gamma. Then we looked at what experiment led to the discovery of the nucleus, so that was talking about the gold foiled experiment, and finding that some alpha went all the way through, but some alpha got reflected back. And then Rutherford proposed that there must be some positive charge in the gold foil, and therefore some positive charge in all atoms to make it repel the positive alpha. Then we said what was the first model of the atom that the scientists believe, and this was the plum pudding model. So that's having a kind of sphere of positive charge and little electrons dotted around it to represent the plums. So scientists believed that, and then Bohr came along and said, no, that's wrong. Actually, it's a sphere in the inside of positive charge, so we're still keeping that sphere of positive charge, but instead we're going to have our electrons orbiting around it in shells. And so he said that each of these electron shells have a specific energy value, and a specific distance from the nucleus. And then they all believed Bohr's model, and then the final thing that scientists came to find is that actually the mass is too heavy if it was only going to be protons and electrons, so there must be some missing mass. And they proposed this idea of a neutron, which is a non-charged particle, completely neutral particle, that has mass, the same mass as a proton. So now we have our final model of the nucleus and the atom, which is that the nucleus is positive and negative charges, a sphere in the middle, a mixture of both. And then we have electrons orbiting around it. And then we looked at what is the nature of beta and alpha and gamma decay. Well, beta decay is just an electron, and alpha decay is a helium nucleus, not a helium atom, helium nucleus. In beta decay, our proton number goes up by 1. In alpha decay, our proton number goes down by 2, and our mass number goes down by 4. What is the relative mass and charge of the proton, neutron, and electron? Well, the proton is +1, neutron is 0, and the electron is -1 for their charges. For the mass, the proton is 1, the neutron is 1, and the electron is 0, because it's so small that we don't count it. An isotope is 2 versions of the same element, let's say carbon, which have the same number of protons, but a different number of neutrons, and therefore a different mass number. Because remember, the mass number, the top number, is neutrons plus protons, and the bottom number is just protons. So these are isotopes of carbon, carbon-13 and carbon-12. And what that means is one of those carbons has 7 neutrons, one of those carbons has 6 neutrons. So they are isotopes of each other. Different number of neutrons, same number of protons. So why are some substances radioactive? Well, it all depends on their nucleus. Is their nucleus stable? Is their nucleus unstable? If the nucleus is unstable, it will release radioactivity to make it more stable. Then on Wednesday, we went a bit further and we looked at penetrating power and ionizing power. So how we can compare the three types of radiation using these features. So we talked about how gamma has the highest penetrating power out of all three. So it has the highest penetrating power. It can get through lots of materials easier than alpha can. So remember, alpha gets blocked by paper. It's really weak penetrating. Then ionizing power is their ability to create an ion out of an atom. And an ion is just a charged particle. So it's their ability to knock electrons out of their atom and make it charged. And the radiation which has the highest ionizing power of all of them is alpha. Then we talked about using the appropriate type of radiation. So for a smoke alarm, we talked about how we would use alpha, and this would be the best kind of choice because it is so ionizing and it is able to create that current. With metal foil, we used beta so that we can measure the thickness and see how much beta we get through the metal foil. Then we looked at activity, which is how many decays we have per second. It's the same thing as count rate. And then half-life. Now, half-life is the amount of time it takes for the number of particles to half, or the activity to half. So it's either the number of particles n, or the activity to half. So it can be talked about either in terms of number of particles or in terms of activity. Either way, it is the amount of time that it takes to half it. So it's not actually half of the decay. It's not half of the time that it takes to do its whole decay, because we don't know that. It's the time that it takes to half its number of particles, or half its activity. Okay, so let's have a little quiz, because we haven't done one of those in ages. As always, it's roughly 16 questions today, and you're gonna have 20 seconds per question, but they are multiple choice. So yeah. Okay, so hopefully you should all be able to join using this game code. So you just want to go to this website. If you guys haven't done a quiz with me before, you just want to type in to either your smartphone, or you can do it on your laptop or your computer, whatever you're watching this on. Type in joinmyquiz.com and then type in the game code 949052. I'm also going to put the link on our Zoom chat so that you can access it straight from there. Okay, so the link is on the Zoom chat. Hopefully you should all be able to see that. If you like, you can just go through that link. Otherwise, type in joinmyquiz.com into your search bar at the top here and type in the game code. So we'll just wait for a few more people to join. Okay, we've got 16 of you, but there's 34 participants, so let's wait for a few more people. Okay, we've got 21 of us on. Um, so I think we'll start. If you guys want to join halfway through, you can just use the link in the Zoom chat. So all multiple choice questions. Don't worry if you get some of them wrong. We'll be going through the answers at the end. It is kind of a hard quiz because obviously we did this content a week ago. So yeah, don't worry about it. Well done to Smart Dude, who's in the lead. Oh, it's been taken over by Max Kieran. Okay, 1 more minute. Try and get as many questions as you can done. Some of you already finished, which is great. Twenty seconds. Okay, let's go through the answers. So, well done to Jess, Max, Kieran, and Terminator, who were top 3. Okay, what is a beta particle made of? A beta particle is simply an electron. That's all it is. It's just a fancy name for an electron being emitted out of a nucleus. Of the main types of radiation emitted from naturally radioactive isotopes, which is the hardest to block? So the hardest to block is gamma. Gamma can get through lots of different materials. It's only blocked by lead and concrete. So well done, everyone. Got that really good. Only one person got that wrong. What is emitted during beta radiation? Same as before, a high energy electron. So interesting that we got 13 incorrect here and 6 incorrect here. So all it is just a high energy electron, just an electron. Gamma changes the atomic number. Now, gamma is an electromagnetic wave. Okay, so all it is a wave. It's not particles, it's just simply a wave. So it looks like this. And because it has this nature, we say that it doesn't have any protons, it doesn't have any neutrons, it doesn't have any electrons. So it does not change the atomic number and it does not change the mass number. So that would be false. What is emitted during alpha radiation? Okay, so alpha radiation is a helium nuclei, not a helium atom. It's only the nuclei, doesn't include the electrons. This one was slightly harder. What is radioactive decay? Radioactive decay is the spontaneous breakdown of an atomic nucleus in a release of energy only. Which type of nuclear radiation is being emitted in this equation? So we can see that we have 0 minus 1e. Now that is the symbol for an electron and therefore beta. When does radioactive decay occur? That's when the nucleus of an isotope is unstable and it gives out decay to make it more stable. Isotopes of the same element have a different number of neutrons, same number of protons. Complete the nuclear equation and determine the decay that is occurring in this reaction. So we can see that the mass number changes by 4 and the atomic number changes by 2. And if the mass number changes by 4 and the atomic number changes by 2, that is representative of an alpha particle. So it would look something like this: alpha 4 2. So we can see that 222 add 4 is 226 and 86 add 2 is 88. So we know that it must be an alpha particle being emitted. How many protons does this gold atom have? Well, that's the atomic number, which is 79. Bit of a trick question there because it is up high, but different periodic tables do it differently. And this would actually be the mass number. So the mass number in general is just the highest number. So the higher number will always be the mass number, the atomic number will always be the lower number. Except for the instance of hydrogen where they're both 1. What is the mass of an alpha particle? The mass of an alpha particle is 4. So remember, it looks like 4 to alpha or 4 to helium. Either way that you choose to draw it is fine, but you should know that this is the mass number at the top. The atomic number is the one at the bottom. The mass number is the number of protons plus the neutrons, and the atomic number is just the number of protons. Okay, what is the definition of an isotope? An isotope, again, is an atom with a different number of neutrons from what is in the periodic table. So different number of neutrons, same number of protons. Neutrons have no net electric charge. Neutrons are neutral. What is the number of neutrons in cesium? Okay, so to find the number of neutrons, N, we do the mass number minus the proton number. And when we do 139 minus 55, we get 84. Okay, so if you said 84, that would be correct. And then the atomic number of a given element is equivalent to which of the following? The atomic number is the proton number, just the proton number. Okay, so we might try that quiz again tomorrow and see if we can better our score. Right now we've got an accuracy of 66%, which is really good, but let's see if we can push it even higher tomorrow. Okay, so let's go on to the main content of today, which is radiation in medicine. So radiation in medicine can be used either to treat illnesses or to track illnesses. So it can be used as a treatment or a tracker. But either way, we must choose the correct isotope, okay, the correct isotope that has the correct radiation being emitted and the correct half-life. So let us look at our first one, radioactive traces. We're going to look at 4 different types of ways that radiation can be used in medicine. First one is radioactive traces. So radioactive traces trace the flow of a substance through an organ. So you can see that this person has got these detectors on her, and these are on her kidneys. So it's to trace the flow of a substance through the organ. Now, this substance emits gamma. It emits gamma radiation, which can be detected outside of the body. Okay, so we put some sort of tracer, they swallow it, drinking some water, it's in the water, and it emits gamma. That gamma can then be detected outside the body using detectors. So one example of radioactive traces is iodine being used for kidneys. So what happens is the patient swallows or drinks some water which contains this radioactive substance. The detector is then placed against the kidney, as we see here. Now, if the kidney is working normally, the substance flows into the kidney and flows back out. And the reading goes up and back down. However, if the kidney is blocked, the reading goes up and stays up because the iodine goes into the kidney and never comes back out. So we know that there is some blockage in the kidney if it's not allowing this iodine to get back out. And the way that we tell that is if the reading goes up and it stays up. Now, this is because the substance goes in and does not come back out. Iodine in specific is used because it has a half-life of 8 days. So remember, a half-life of 8 days means that after 8 days, the number of particles that we had at the beginning is halved. Iodine also emits gamma, which is good because then we can detect it, and it decays into a stable product, so it's not going to be harmful for the patient. The second application is gamma cameras. So gamma cameras take pictures of organs. That's their job. So we need to take pictures of organs to see if there might be some kind of defective part of the organ. So what happens is the patient is injected with a solution that contains a gamma emitting isotope. So they take some sort of gamma emitting isotope, whatever that might be, they put it in a syringe and they inject the patient into that organ. The solution is absorbed by the organ and a nearby gamma camera detects the radiation being emitted from the organ. Now, gamma rays pass through holes in a lead grid in front of the detector. So this is the lead grid here, and there are holes which it can go through. These are the holes here. Now, detectors only detect gamma rays from nuclei in front of it. So it's only going to detect these ones because they are right in front of it. They're completely in the organ. Now, the half-life of the isotope is long enough for the picture to be taken, but it's short enough so that it decays and is not harmful to the patient. Third one is gamma radiation being used for radiotherapy. So if we have a narrow beam of gamma, that can destroy cancerous cells. So we shoot the gamma at the cancerous cells, and this can destroy them. What we use for this process is an isotope of cobalt. Okay, so an isotope of cobalt. Now we use cobalt because it has a half-life of 5 years. So after 5 years, that radiation will half, and after 5 years, it will half again, and so on and so forth. And so that it will no longer be in the patient's body. And the reason that we use cobalt is because it emits gamma. And as we know, gamma has the highest penetrating power and can penetrate deeper than alpha or beta. And the final one is radioactive implants. So we can implant radioactive substances to destroy cancer cells or bigger clumps of cancer cells, tumours. So we either use beta or gamma emitting isotopes and we implant them into the place which has the cancer. And this can either be in the form of small seeds or tiny rods. So that's what the implant looks like. Now, permanent implants use isotopes with half-lives that are long enough to irradiate the tumour over a given time. So let's say we want to irradiate the tumour over a month. The half-life needs to be long enough so that we are able to do that, and short enough so that they decay soon after that. So how can we reduce our risk? Well, everybody is exposed to radiation, whether we like it or not. Everybody has some exposure to radiation. This comes from nuclear power plants, it comes from cosmic microwave background radiation, it comes from food, all sorts of things. So everybody is exposed, but it's such a tiny amount that the risk is next to nothing. However, in high-risk areas, such as nuclear power plants or places where they're working on nuclear reactors, they have to wear radiation monitors and take extra precautions and wear like personal protective equipment. Okay, so moving on to the next part of the content, nuclear fission. So nuclear fission is this idea that we split a nucleus into two smaller nuclei. So we have a nucleus and it goes into two smaller nuclei. This is called fission, the breaking down of a nuclei. So energy is released in a nuclear reactor because of fission. So when we do this fission process, when we break down this nucleus into two smaller nucleuses, we also have some energy being emitted. So not only do we get these two smaller nuclei, we also get some amount of energy which is being emitted. Now, the reason that fission happens is because this nucleus is struck by a neutron. So it's struck by our neutron, our uncharged particle, and this is what causes it to split into those two nuclei. When that happens, we also get the emission of even more neutrons. Now, these neutrons here are called fission neutrons. They are the neutrons which are a product of fission. So this one and this one are called fission neutrons. Okay, so we have our process. We get a neutron striking a nucleus. That nucleus splits into two smaller nuclei. And when that happens, we don't only get the smaller nuclei, we also get some neutrons and some energy being released. Now, fission can happen sometimes without a neutron being absorbed. So sometimes it doesn't need this neutron to strike it to start the fission process. Sometimes it can do it spontaneously, and that's called spontaneous fission. That's fission without a neutron. So fission neutrons, they're usually 2 or 3 neutrons, and they're released at high speeds. So when we get this breaking down of the nucleus into 2 smaller nuclei, we also get these neutrons, as we know. Now, it's usually 2 or 3. We'll just do 3. As we know, these are called fission neutrons. Now, these are at very high speeds. They have a high velocity. And we also get this energy, which is in the form of gamma radiation. So now we know more things about this process, which is that usually it's either going to be 2 or 3 neutrons, they're at high speeds, and the energy that is being released is actually in the form of gamma radiation. So now we know the whole fission process. Let's look at chain reactions. So we know that fission happens, and fission can keep happening. We start with 1 nuclei, and it splits into 2 nuclei. Those nuclei can then be split into 2 further nuclei, and so on and so forth. This can keep happening, but only if we keep getting neutrons striking. So at every single point, there must be some neutron striking it. Now, a fission event we know releases neutrons. As we can see here, we get the neutron striking the nucleus and it releases neutrons. This causes the nuclei to split, as we know, and neutrons are released. These are the neutrons that are released. And the process repeats. Those neutrons then strike more nuclei and more neutrons are released. Those neutrons then strike more nuclei and more neutrons are released. And the whole process repeats. So the neutrons that are released are then used to strike more nuclei. In a nuclear fission reactor, 1 fission neutron, so one of these, produces 1 more event of fission. As we can see here, 1 neutron produces 1 more fission event. 1 neutron, 1 fission event. 1 neutron, 1 fission event. So every neutron that is released goes on to produce another fission event. And you can see that this process goes on forever. So each of these fission neutrons will go on to produce their own events. Okay, so we know that fission occurs, and we know that fission occurs in nuclei, but it only happens in certain nuclei, in certain isotopes. So in a nuclear reactor, we must have fissionable isotopes. Fissionable isotopes. We can't just have any random isotope, it must be fissionable. So examples of ones that are used in in real life are uranium-238 and uranium-235. So a small percentage of uranium-235, but mostly uranium-238. Okay, so I've been talking about this idea of a nuclear reactor, and a nuclear reactor is exactly where fission happens. So this is our nuclear reactor here. So what we have is fuel rods of uranium spaced out evenly in the core, and that is these ones here. These are fuel rods of uranium. So we put our uranium into the reactor core. This is the reactor core here. Now that reactor core contains fuel rods, control rods, and water at high pressure. The fission neutrons are slowed down because of collisions with atoms in the water, and therefore we can call the water a moderator. So the water acts as a kind of thing that slows down the fission neutrons, because fission neutrons go too fast for us to be able to create more fission events. So as we see here, these neutrons have a high velocity. Okay, fission neutrons, these ones or these ones, have a high velocity. And we don't want them to have a high velocity. We want to slow them down. And the reason that we want to slow them down is because they can then be used in fission events, in new fission events. High velocity neutrons are useless. They do not produce more fission events. The only way that we can keep producing fission events is by slowing our neutrons down. And the way that we slow our neutrons down is with water. And water does this because it collides with those neutrons and makes them slow down. So the features of a nuclear reactor, well, the water is a moderator because it slows them down, as we know. The control rods absorb surplus neutrons. So the control rods that we saw in our diagram absorb surplus neutrons. That's why they're there. The depth of the rods in the core is adjusted to maintain the chain reaction. The reactor core is a vessel made of thick steel to withstand high temperatures and high pressures. And the vessel is surrounded by concrete walls which absorb the radiation and make it safe for anyone outside. So those fuel rods can get really hot. And not only does the water act as a moderator, but it also acts as a coolant. And it cools this whole thing down. The water is pumped through the core and it goes through sealed pipes to and from a heat exchanger outside the source. So you can see it goes to a heat exchanger, and then it takes the water transfers the energy from the core to the heat exchanger. So it takes all this heat and it exchanges it with the heat exchanger. So it gets water coming in, which gets heats up and goes into here. That water then cools down, makes a coolant, and it comes back and the process repeats. Okay, so that's all the content that we had to cover today. I'm going to go through a few questions before we start our example questions. Okay, so someone says that they don't understand what half-life is. So let's go all the way back to half-life and remember what half-life is. So let's say we have a graph of time against the number of nuclei, and we have some decay curve. Let's say that this is at time 0, and at time 0 we have 100 nuclei. We want to find the time that it takes to get to 50 nuclei, or for the nuclei to be halved. And therefore, draw a line across to our decay curve and a line down, and we might find that it takes 10 seconds. So the half-life is 10 seconds because it takes 10 seconds for the number of nuclei to half. Emission just means giving out, releasing, rejecting. So one second, go back to slide 3. What does irradiate mean? Irradiate just means to put radiation on something. Decay means to give out some sort of radiation, whether that be alpha, beta, or gamma. Decay is just a nucleus giving out this radiation. This is AQA. I always do my lessons based off AQA. Is there a delta particle? No. Is gamma radiation harmful to your body? This is an interesting question. Gamma radiation can be harmful to your body, but it depends on how much and how long. Okay, so how long you're exposed to the gamma radiation and how much gamma radiation you're being exposed to. So it can be used for medicinal purposes, but only if we use the correct dose and exposure. If we get that dose and exposure wrong, it can be harmful. But the way that they use it in medicine won't be harmful. Okay, I think that might be all the questions. Why does it need to be split? Okay, so fission happens so that we can create energy. Okay, so this is the idea, is creating energy. Fission is the breaking down of nuclei, and tomorrow we're going to be looking at fusion, which is the joining of nuclei. So we have two things, fission and fusion. Okay, so let's try some practice questions. These are a mixture of all the topics that we've covered so far. So this diagram represents an atom of lithium. And you can see that we've got electrons, we've got protons, and we've got neutrons. Now, what do we think the number of protons is, the number of electrons is, and the number of neutrons is? What do we think? Looking at our atom of lithium, what's the number of electrons, the number of protons, and the number of neutrons? Put your answers in the chat. What do you think? So remember, Bohr said that electrons orbit the nucleus in shells. So we know that these must be our electrons. So we know that there are 3 electrons, 3 protons, and 4 neutrons. Okay, now what you might be confused about is we know that there are neutrons and protons in the core. Okay, so the nucleus is made up of neutrons and protons. But how did I know that it was 4 neutrons and 3 protons? It could have been 3 neutrons and 4 protons. So how did I know? Well, there's something that I've not told you yet, which is that the number of protons and the number of electrons is equal, always, unless it's an ion. So for a normal atom, for a normal element, for a normal particle, the number of protons and the number of electrons is the same. Okay, so that's how I knew that the white dots were the protons and the black dots were the neutrons. So the number of protons and electrons is the same. Okay, so here's another one, beryllium. And the three types of particle that make up the atom have been labelled this time. So you've been told that on the shell, they are electrons, the white dots are neutrons, and black dots are protons this time. Use the labels from the diagram to complete the following statements. The particle with a positive charge is what? The particle with the smallest mass is what? And the particle with no charge is what? What fills in those gaps? Using either electron, neutron, or proton. Okay, so what do we think? Which one is the particle with positive charge? Which one is the particle with the smallest mass? And which one is the particle with no charge? Particle with a positive charge is a proton. How I like to remember it is because they both begin with a P. So positive charge is a proton. Particle with the smallest mass is an electron. And the particle with no charge is a neutron. Okay, here we've got a helium atom. You've been told K, L, and M, and N. You've been given 4 labels, and you need to decide which is the electron and which is the same as an alpha particle. This is a helium atom, not a helium nuclei, a helium atom. Which bit is the helium nuclei, and therefore the alpha particle, and which bit is the electron? So we know that the electron must be L because it's sat on the shell. And the part of the atom which is the same as an alpha particle is the nucleus. Okay, this is the nucleus here. This is an alpha particle. And the reason that it's only this bit is because alpha is the helium nucleus and it doesn't include the electrons. So the part of the atom that the alpha particle would be is M. Okay, let's try some. Okay, so radiation from radioactive sources is used for different purposes. Identify the type of radiation you would use and give a reason for your choice. What radiation would you use for obtaining an image of an internal organ? And what radiation would you use for finding out whether a kidney in a patient is blocked? And why? Have a think. I'll give you 2 minutes to have a think about what radiation you'd use and why. Put your answers in the chat or just have a think to yourselves. Okay, so to obtain an image of an internal organ, we tend to use gamma cameras. And for tracers, we tend to also use a isotope which emits gamma. Gamma tends to be used because it can be detected outside of the body. Okay, what are two sources of background radiation that originate in your environment? So where can background radiation come from? Everyone is exposed to radiation, but where does that radiation come from? So where does background radiation come from? Have a think. Okay, so radiation can come from lots of different places. It can come from inhalation, because we have radon in our air. It can come from food and drink. It can come from rocks and soil. It can come from cosmic microwave background radiation, which is the radiation that was created in the Big Bang. It can come from nuclear power plants. And yeah, that all happens in different percentages. The main source of radiation is from radon in our air, which is a radioactive element. So this is the main source, and it creates most of what we know as background radiation. Okay, what is one type of radiation which is emitted by a radioactive implant? So there's two types which can be emitted by an implant. What are those two types? Okay, yeah, so beta and gamma are the two radiations which are emitted by a radioactive implant. Notice that alpha is not really used in medicine, and the reason for that is because alpha is so weakly penetrating and it can't really get through the skin and through organs. Remember, it can be stopped by a piece of paper, so it's got no chance of helping us and getting through the body and helping us to understand illnesses in the body. So alpha doesn't tend to be used. Most cases it's going to be gamma, and that is because it is just so penetrating. Okay, and then explain why a radioactive isotope is used in a kidney scan, and why should it have a half-life that's not too short and not too long? So it needs to have this kind of balance of half-life where it's not too short and not too long. And that's the same with any isotope being used in medicine. It needs to be long enough so that we can detect it and take a picture of it. So it needs to be long enough so that we can detect it before it decays, but it needs to be short enough so that it can decay after we've taken the image and not harm the patient and not stay in there for a long time. Because as I said, the amount of harm that radiation can do to you doesn't just depend on the dosage, it also depends on the time that you're exposed for it. So we need to have one that is not too short so that we can take the image and not too long so that it decays quick enough. Okay, so we'll stop there for today. Tomorrow we're going to be looking at more to do with nuclear radiation and specifically nuclear fusion. So today we looked at fission. Tomorrow we're going to be looking at fusion, and we're going to be doing lots and lots of exam practice after that in the form of quizzes and the form of exam questions. So as always, this has been recorded and it will be uploaded onto YouTube later. If you guys do want any kind of one-to-one, more personal tutoring with a tutor like myself, then that is something that MyTutor offers and that you guys would be able to access. So just go onto the MyTutor website to have a look. Okay, so I think that's everything that we're going to cover for today, and I'll see you guys tomorrow at 2 for another physics webinar. Thank you. Bye.